Can you
Professor Watada.
disconnect the share
Good
screen?
morning.
Okay, thank you. Hi, good morning.
How are you?
All of you.
Yeah, I'm fine. Yeah.
Yeah,
nice to meet you. Yes. Yeah.
Professor Cho, do you use the share screen? Do you use the share screen? No?
Says free. Sorry. I can see you. It's everybody, and so very nice. Very nice. Congratulations. Yeah. Okay. How are you, Professor Watada?
Okay, good morning. All of you.
Good morning, everybody.
We would like to start FIM, IMIP, UMSO, simulation and optimization. So this is the chair, one of the chairs of this conference. I'd like to give the opening messages. All delegations and friends, we are very pleased to welcome you at Kitakyushu. This site is based on Kitakyushu, but the Zoom is coming from Malaysia because of this was organized starting from Malaysia, but Corona make the conference moving to the Kitakyushu. So Kitakyushu city is 200 industry years for the multilateral so the FIM-IMIP-UMSO2021 is the 29th virtual international conference of Forum for Interdisciplinary Mathematics, Statistics, and Computational Techniques. It is the abbreviated IMSCT 2021 FIM. FIM is Forum for Interdisciplinary Mathematics. And IMIP is the International Symposium on Innovative Management Information and Production. So the around 14th symposium this time. And UMSO is the International Conference on Unconventional Modeling. This is coming from the Malaysia. So this third or fourth UMSO conference. Originally, it is geology, but geological people do not like to attend so many. So we focused on unconventional modeling. So it is quite interesting. The conference is organized by the International Society of Management, ISMEV. You can see it, the homepage, and Graduate School of Information Production and System, Waseda University. I'm right now visiting the researcher of this Central Research Center. So the Kitakyushu is located at the historical center again, originally coal mining and iron industry till 1970, almost the 150 years. Today, the industries of Kitakyushu are expanding to automobile manufacturing and the how can I say, the software and the environmental industry. So the another point, this place, you are not here, but the population of Kitakyushu city has approximately 1 million inhabitants. More industrial peoples live here. The history of Kitakyushu can be back to Heike story, 1000 AD. Quite a famous history story in Japan. You may read this story in English, but the city itself today is more future-oriented. Waseda University, multimedia, and also this conference is organized by supported by Waseda University, Multimedia University, Malacca, Malaysia, and Zhejiang Gunshan University, China. So the Mojiko is beside the city to Kitakyushu. The Mojiko is the harbor which was center of shipping in the past industries. So it is quite a famous story that Albert Einstein received the information of Nobel Prize Award some years ago on a shipboard coming to Kitakyushu. You'll find such records of Albert Einstein in Mojiko Harbor, as well as chance to buy some souvenirs. So some people attended some conferences here. And also we would like to emphasize some post-publication special issue of various journals. One is Mathematicae Japonica of 45 years history. FIM-JISS is the main official journal of FIM. It's also has the 45 years history, but the volume is 40. Recently 46, and JACIII ESCI Q4 journal, and we also organize a special issue for MDPI, the mathematics, IJERH, and FinTech, 3 journals. So you can submit your papers to this journal. Of course, you can submit another paper if it is innovative. So I would like to assign to next message from Professor Bishi. Professor Bishi, can you give the speech? I will disconnect.
はい、good morning.
Your sound is not coming. Please switch on at the microphone left side. Can you find your speaker button on the screen? Your microphone is not ready.
Good morning. Here. This is innovative management information production that over past 20 years and conference have been.
Not yet. Your voice does not come.
This is over.
Later, I will assign. I move to the next person.
Next,
Professor Yabuchi, are you available?
Yes. Yes.
Please give your.
Yes. Okay. Good morning, everyone. I'm Yoshiyuki Yabuchi, Shimonoseki City University, and one of the co-chairs of this conference. I'm
Your
the
voice
third.
does not.
Oh, really? Good morning. Hear my voice? No? Oh. No?
We can hear you. So.
Oh, thank you. Thank you. Good morning, everyone. I'm Yoshiyuki Yabuchi. I'm one of the co-chairs of this conference. I'm third greeting today, so I have no I have no left time. So I will talk briefly. This conference is held online and is programmed.
Yabuchi, your voice
Yes.
is quite low. Please louder.
He is clear, sir.
Clear. Yeah. This conference is programmed from 9 a.m. to 10 p.m. Japan Standard Time. So please take care of your own health and enjoy this conference. We will explain the special issues after the last session of this conference. So if you have interested, please listen to the explain. Thank you.
Thank you very much. So may I move to the Professor Vinci? I think my the speaker was switched off. So sorry. Please, can you restart? Professor Vinci, can you restart? Professor Vinci, are you there?
There.
Yeah, please, please speak your message again.
Okay. Here.
I can hear.
I'm Ding Xi. This conference information production over past 20 years, and conference being held in most part past and Oceania. This is here. The next year, the IMP in the Nanjing, China, welcome the CEO next year. Okay, thank you. Thank you. Watada. Thank you. Watada.
Okay.
Okay.
Thank you very much, Professor Vinci. I move to Professor Wentao Gu. Are you there, Professor Wentao Gu? Not yet. So first I move to Professor S.C. Tang. Would you give a message from co-chair from Professor S.C. Tang? Are you there?
Yes, Prof. Watada, I'm here. Good morning to everyone from Malaysia. Okay, my name is Tan. I'm one of the co-chair of this conference. It's actually my pleasure to be one of the co-chair of this conference. And there's just a short message from me that I hope everyone will enjoy and wish you all have a fruitful discussion throughout this conference. Thank you.
Thank you very much, Professor Tang. So I check Professor, oh yeah, Professor Wendell, would you give your message for us? Thank you. Please. I think the microphone is not switch on the screen, microphone. Looks microphone is switch off. Yeah, right now it's okay. Please speak. But the voice does not come. Switch is okay, but the voice does not come. So no, voice does not come. Okay. Maybe microphone condition is not good.
I see. Hello?
Yes,
Hello?
yes, audible now.
Yeah,
audible.
it's okay.
Oh, okay. Hi, everyone. It is my honor to be the co-chair of FIM-IMIP and UMSO 2021. And on behalf of the Quantitative Economics Institute of Zhejiang Gongsan University in China, which is one of the organizers, I'm honored to welcome you all here for exchanging the knowledge of academic and sharing ideas. And I'm truly proud of our international conference, which got to show constant interest in the information science and management issues across many fields and different countries. Finally, please allow me to express my sincere appreciation to Dr. Watada and Dr. Tam for their great efforts of organizing the conference, and also my sincere appreciation to you all present for this online conference. And I'm confident that it will be an informative and enjoyable event. Thanks. Okay. Dr. Watada, I'm done.
Yeah, okay. Okay, thank you very much, Professor Wendell Group. So we would like to finish the opening message, and we would like to go to the plenary session. The first plenary session is the Professor Toshio Fukuda, quite a famous person. You can find that before starting, I would like to introduce him. So I would like to make him to start just 9:30. So the Professor Toshio Fukuda obtained the bachelor degree from Waseda University, Tokyo, Japan, in 1971, and he studied a master program at Tokyo University, and he studied graduate school of Yale after that, and joined the school Science University of Tokyo, and then after obtaining a PhD degree at Tokyo University, he moved to Nagoya University, and his activity is quite famous, and maybe mechatronics. Recently, he is working on the cell computers. He showed his research result today, and he obtained various the awards and the medals. I introduced several. He was the president of I2P Robotics and Automation Society, and also the director of the I2P division, the system and control, the founding president of I2P Nanotechnology Council. He was director of Region 10, and Region 10 is Asian areas I2P chapter. The director I2P Division X systems and control, Division 10 means, and I2P. Right now, he is the I2P president from 2020. He was editor-in-chief of I2P ASME transaction on mechatronics, and he was the founding general chair I2P International Conference on Intelligent Robots and Systems. And he obtained the various awards. I showed several out of them. So he received I2P Eugene Mitterman Achievement Award in 1997, I2P Third Millennium Medal in 2000, Humboldt Prize in 2002, I2P Robotics and Automation Pioneer Award, I2P Transaction Automation Science and Engineering Google Best New Application Paper Award, and George Salidis Leadership Award in Robotics and Automation in 2009, I2P Robotics and Automation Technical Field Award. And he also he obtained the IROS Harashima Award. Professor Harashima is a famous, he was a famous professor of Tokyo University. Right now, the Professor Emeritus. So he obtained this named award, and the IROS Distinguished Service Award, Medal of Honor with the Purple Ribbon from Japanese government 2015. Following member, right now is foreign member of Chinese Academy of Science. So may I ask Professor Toshio Fukuda to start your speech? Are you ready?
Watada Sensei, I can. Oh, okay. Fukuda Sensei joined now. Yeah, he's muted. So just if you unmute him. Hi.
Okay, you will speak for the Professor Fukuda. Is it correct?
I'm here. I'm here. Hi, Chetan. Hi. Hi, Watada-san. Sensei, how are you?
All welcome you very much. So we are waiting for your speech. Please start right now.
Okay. May I share the slide? It's okay. Can you see my slide?
Yeah, we can recognize your.
Okay, thank you very much.
Okay, please.
Okay, may I start? Okay, so I'm Toshio Fukuda. I was the president to the 20 ITP, the president, and to the 21 this year ITP past president. So far, thank you very much for your support. I could enjoy my life so far. And I talk about such a micro nano here today. So these are my students so far work together with me. That's great to work together. So they are my PhD students so far, and that's great. And then this another one. Oh, there's a new one. Maybe I have now 105. This is 105 PhD students so far. So my research work was multi-scale robotics that you can hear. So like I dreamed like make a robot, such a from module robot to the robot group of robot, and many robots together, swarm robotics. That can like a biological system, the cell and the organ, animal, then society, human being. So I tried to make it. So now I made such a robot system. Now I'm interested back to biological system and combine both of them as a hybrid system. So that's interesting. So yeah, that's like my work so far, like a monkey robot. I work as a multi-locomotion robot here. Also micro nano robotics and some others. So that the micro nano robotics mechatronics have many kind of aspect. So this is my summary of those things. What I'm going to talk today, particularly talk about such a kind of micro areas here, micro bio areas here today in these areas. So micro nano robotics is a kind of wide scope, and many people working in this field. The micro nano robot here. So anyway, this is something here, particularly interesting in vitro realization. Oops. Okay, in vitro realization of for such a kind of 3D tissue or some many others. So like a micro nano measurement or micro nano manipulation or micro nano assembly, we have many kind of aspects. One example, like a dynamic interaction between multiple cells in the such a measurement or some injection sanction devices to interact with biological cell. It's a micro nano manipulation or construction of artificial cell. It's a kind of part of micro nano assembly here. So particularly recently, I'm also interested in such a kind of manipulation of C. elegans. These are small kind of biological organs that are less than 1 millimeters, and it has some special kind of characteristic, some like a kind of taxis. So it's like here in biological here. Here, so they move like this is very, very small, like such kind of things. It's a model organ, and then it has a such kind of C. elegans. So it has a very special chemical taxis. So here looks like here, they move here, and they are very, very good at such a kind of smelling, better than a dog. So that they like such a kind of smell of such a kind of cancer, for example. So we can use this one as an indicator or biological indicator to detect cell, such a cancer by using human urination. So once you can give me a PPs, I can dilute 1/10 or something like that, then I can use those things here for those things. If somebody is, has a cancer, then these C. elegans go to such a kind of direction of the person's urination. That's kind of interest here. This kind of biological intelligence here. Also like here, we can inject such a here small one and to detect such a kind of some neuron experiment. Also like kind of stiffness measurement, many others. So these are very, very nice kind of devices here, kind of organs, model organs. So I can use such a kind of C. elegans for many, many things. And then I try to use such, manipulate such a C. elegans. So C. elegans, why C. elegans? Maybe you have those things. If you have accident, nerve system damage, your disability. But this C. elegans has some special ability that the nerve system, once we cut it, but still it can make it, rebuild it, such a system. So that's very interesting. That's so many scientists working in those things. So we made such a kind of injection system here, C. elegans here, go over such a devices here, then they come here and just sunk and hold it here. Then we can give us such a kind of tool here, micro beads, then release it here. So that's the kind of thing here. So once he come here, stop it here, injected it here, then release it, come here, like this. So this is a kind of manipulation, micro manipulation for C. elegans. So this is a reality here, make it such a thing here, then do that, something like that here. This is very nice. And positioning of C. elegans in the micro channel, make it so thing here. So that's good, nice. This is kind of nice to see that. So this is a kind of some kind of special devices, micro nano manipulation. So this is moving here. So you can see some here happening. So this is some small like micro manipulation. And I like such a kind of multi-scale manipulation technology for works for nano to macro. In such a kind here, like for biological system. In biological cell wise, so we can make artificial cell model, we can give input, then we can get the output, expression control, then observation and measurement, we can go into feedback here. So we can give another environment control stimulation or gene manipulation here. So this is a kind of feedback here. Also, like here, like some kind of more other devices here, medical device input here, output, then we can make a function control. Function control, so for example, this is a blood vessel that we observe it, the measured interval goes here. So we can see how the kind of blood vessel grow according to your kind of physical motion. So that's a kind of shear force going up here. If it's a shear force more because of the increase of blood, then the shear force is getting bigger. So they try to reduce the shear force. So that kind of diameter of blood vessel going to bigger and bigger. So that's a kind of mechanism. There's a messengers here inside. So that's a medical doctor created those things. That's a nice to those things. Also like here in the nano micro or centimeter level, that's such a kind of cell, artificial cell model, and gene expression control, induction indifference. Each we can have a control like a expression control, local environment control, or function control. So that's nice to have those in here, as I mentioned. So single cell and nanosurgery is an injection, extraction, diagnosis, cutting, embed. That's a nice to have those kind of things here. For single cell, we can have those in here. Zero assembly, degree of one-dimensional assembly, second two-dimensional assembly here. So we can make some other like here. We can do that. So that's a 3D cellular system here. We can make those things. Regeneration engineering, biologic simulator, or investigation cellular system here. That's a good thing here, and particularly here, regeneration engineering or biologic stimulation. We can work with medical doctors. Recently, I'm interested in cyborg and bionic system. Anyway, that's a good thing. For example, this is a kind of my can work for or such a kind of microsurgery for blood vessel. So that's a kind of my product and commercial product for my lab to make such a kind of simulator, so EVE system here. So that's a blood vessel simulator. Now, how to make such a kind of regeneration system, and then try to make a super simulator. That's a kind of interest to do so. So what I'm doing here is to say like we can make such a kind of blood vessel here, for example, cell here. Then we can put it here. Then we can make it such evaluation in the clinical form. So in a sense, kind of from such a kind of biological cell with bottom-up approach, from here, that's a kind of many methods. For example, then you can see like a sushi roll. We can roll up here, make a such a kind of blood vessel fibers. So this is a top-down approach. So combine with them, we can make such a kind of microassembly. Those here. One example is like I like so far in my research work was such a here, such a on-chip manipulation and cell cultivation. So that's nice to have. Then we can go make it and grow it, harvest it back here to human. So something here, that's a nice one, and I talk about this one, particular. So get a kind of cell, then we can make it on chip fabrication, so make an assembly here, then can culture it, and then we make a kind of construction of cell, then put it back here. That's a kind of thing here. So particularly this structure, what I do is like a micro well here, that's a kind of microchip here. We have such a PDA, PEGDA here, and the go over here. Then one disc, sort of disc. So diameter is 110 micrometer. So inside is the hole, like a donut here, small micro donut. So those kind of cell made here with the objective lens here and fabricate those things on site. Then put it here 1, 2, 3, 4 line up here. Then we can make those things here like this. So make it with a flow here. So we can make those kind of structures. So 1, 2, 3, 4, 5 come here. So maybe we can here. So that's here, come here like this. So that's nice. 1, go 2, 3, 4, 5 like that. The thickness depends on the cell microchip, how you can make it here. So that's sometimes longer, sometimes smaller, something like that. We can make it. So this is a kind of experiment result here. We can make an engineered vascular-like structure here. So this is something here. Also kind of this liver cell here. We can make, we're working on those things. I'll show you such a 3D hepatic lobule module, how we can make it later on. So anyway, that's like a fabrication, microcapsule. We can make it also here. So we can make such kind of calcium, such a kind of cell here. So we can make those here, this small here, like this here. So we can make a kind of a shape likewise, or cubic likewise, or rod-wise. We can make different type of a structure here. So day 1, day 2, you can make such a grow inside, or such a capsule, and the cell is growing inside, like such a rod-wise, sphere-wise. So you can see here, it is still green means it alive here. Okay, so that we can make such kind of fabrication, and nice to see make a different type of kind of lobule structures. So this is some cell, cell is still alive. The lady died, but still is 90% still alive in 44 days here. So maybe we can, with a thickness of cell sheet is about 320 micrometer. We cannot make a big one because if we make bigger, it's a lack of the oxygen, then cell will die. So that's a kind of fabrication. That's nice to prepare here. So there's once again, we can give a kind of a selection of cell here, then make them assembled and incubated here, harvesting, and then go out. This is a kind of biological robotics and automation. Okay, this is nice. So in each there is a devices here. Okay, that's nice to make it. So this is a kind of a hybrid manipulation setup here. This is in my lab here. So that's the ring wise move here. Okay, so that's a manipulator here. Manipulator makes can manipulate here. Once again, this is a 1, 2, 3 manipulate, 1, 2, 3 manipulate, okay, under the microscope. So that's why there's a 1, 2, 3 manipulator under the microscope. That's a great, so they can manipulate in this way, and doesn't work. Okay, anyway, this is a you can make many cells, 1, 2, 3, such like a shish kebab or shibachichi in Europe. You can enjoy such a thing, but it's a micro level. Okay, this is something here. So here is like that. So that we can make it. Okay, so nice to do so. So this is something we can control. This is an image of focal microscope. Okay, anyway, that's nice to have. Then we can have a magnetic hydrogen fiber. Okay, that's we can control those things with magnetic force. So that's a nice 1, 2, 3. Okay, so that's nice to make such kind of manipulation using magnetic force. So this is nice. So then finally we can make this here. So that's a kind of many structure. Particularly here, that's a nice to have such a kind of structure. And one layer, second layer, third layer. Why we make it? If we suggest we don't make such a kind of artificial blood vessel in the layer wise, they die because of lack of such a nutrition. So that's why we make such a kind of 3D structures. So 3D structures, such a nice to make it. So that's a kind of mid-size 3D cellular structure with a vascular network here. And this is a particular how we can make such a 3D vascular network. You can see inside there's a flowing, okay? Flowing. So that's what we try to do. First of all, there's a 1 degree freedom, to 2nd degree, 3 structures. Okay? This then we can see the cell and make a fiber, then we can make a culture like this. This is something. So we make it so here like that. We can pick up, select some liver cell here, put it here, and that's one of the part of them. Then we can make those things here. This is a channel network. This is a kind of a vein and you. This is from the relay. This is your kind of another one here come up here. They get together here. So this is a central vein here. That's interesting. So this is connected to the many such as your intestine in your body. So this is a micro, but the other is going to be more nano level here, like kind of many kind of blood cell. So that's how we try to make it something. Support that's here, we can make it here. So that's one layer, second layer, third layer here. How we can make it here. So that's again here. So that's how we use. We made such a kind of experimental system here. So that's great to do so. So nice to have those here. First one, second one, last like this here. So that's a kind of third, 1, 2, 3 layers, such as structures. And that's nice to have those in here. So the blood vein survive in such a way. And that's because of how we can make it here. So the cell is alive, is still there. That's great. And we can make those in here. Anyway, this is a kind of fabrication, 3D structure here. That's nice, like here. And we made such a hepatic lobule module. Hepatic is for your liver, okay? So to make it here. And so far we made it here. And still we have some problem, but anyway, that's a kind of structures. We can do that. So we can make a millimeter size 3D cell, then achieve high-speed assembly and 3D channel network using such a magnetic field by high-speed assembly or arginate hydrogen fibers for 3D vascular network here. So that's so far. Now once again, this is my kind of experiment equipment. Make those in here so far. Anyway, this is a manipulation of micro objects here. That's a good magnetic field here. That's what I've done so far. Okay, that's here. So that's actually to grow here in this way. IPS here. Okay, so we hope we can use it here in the future, make it an implant and to do so. That's our kind of goal here. And that's great. And we did something like that. So far we did it so far here. And that's kind of nice to have those here. And we analyze why we can make it here. That's a kind of a magnetic field and analyze and studies here and try to make it here, how we can make such a kind of magnetic field larger. So here, like this. And analysis shows that here we can make such a kind of a magnetic field and we can manipulate those kind of magnetic fiber here. Okay, so that's a nice to have those here. And we understand what the kind of here, what we do that. So that's great to see and make many different type of things here. And these are such a kind of, finally come up with these kind of structures. And nice to have those in here. That's a kind of way how we can make such a kind of experiment. And that we are working together, such a kind of structures. And nice to have those here. And we finally we could make those kind of structures, and we publish those kind of paper here. That's my so far done so far, and I like this kind of result. Try to work together for micro nano together, and it's great to work here for the with medical doctors. Okay, so that's the kind of thing, and how we can make such a magnetic field, and that's a more detail, but nice to have those things working together. And that yes, so that's a kind of so far I worked with those things, and this is even project since 1989 when I came from Tokyo to Nagoya, working together those things here. But recently made such a bionic humanoid here, and that's another simulator, and working such like a cybernetic organism here. And maybe I can talk about just a kind of cyborg bearing system, just a couple of minutes here. How we can make such a robot mechanical system, bionic system together, cyborg bearing. So that we can work on those such a symposium here. That's nice. How is a cyborg here? Cyborg is a kind of integration or fusion of such a robot, machine, and animal here. So here we can have a kind of something here, some here sensing, or something here communication, or energy-wise, artificial organ, or something. So we try to contribute this area, artificial organ, what I explained, so in here, how we can make a biological tissues and mass in here. Finally, what we can do is we can connect here with a neuron connection. That's a kind of biological level here, device level, system level control, many ways that we are working on this biological level here. So many things. If you there are many devices by cyborg already. If you have something like artificial muscle or something, you have a kind of hip bone, or kind of you have an artificial arm or leg here, you already have such a biological system already. One example, like an artificial heart, that's one of them. Any alternative device function is already available, installable, deviceable, system level, and that's great to do so. And there are a lot of kind of research here, rich enough to make a big research work here. And that's how we make such a kind of cell here. And this is artificial cell. And we can control 1 hertz, 0.5 hertz. This is a kind of actuators, artificial actuators. Anyway, thank you very much. I worked on 3D cell assembly based on micro nano manipulation technology software, and we could make some of them, not everything, but still it's a rich enough research field, and try to make it more, and more like a direction cyborg and hybrid bionic system. Thank you very much for your listening. Thank you very much.
Thank you very much, Professor Fukuda.
Yes.
We do not have the question and answer, but may I ask 2 questions, 1 minute? So
Okay, go ahead.
How far?
Yes, Watada-san. Hi, dozo.
May I ask you?
Yes.
How far these research were industrialized? Someone explained the industrialized. And another, how do you think your research in future? Would you explain 1 minute?
Yes. That's a nice. Thank you very much, Watada-san, for nice question for commercialization, industrialization. Some of them already there. For example, like kind of artificial blood cell. Yeah, blood cell. For example, less than 4 millimeter is not so easy to make it for those kind of applications so far, but we made it here. So that's nice to work together with a medical doctor. So the company can provide such a small kind of artificial blood cell. But I think this kind of thing is such a kind of artificial intestine kind of devices is need more medical validation. This is kind of research. Need there such a more medical validation for human use. But so far we can use only mouse or something like that. So need it's a kind of basic research. Need 5 years to 10 years more to go. But such a kind of a biological indicator using C. elegans, that's a kind of easy to commercialize. Some of them people may commercialize for detection of cancer.
Thank you very much, Professor Fukuda, in your visit time to join us. Very nice presentation, quite interesting. Thank you very much again. Thank you.
Thank you very much. Thank you very much. I am very happy to see you. You are still active.
Please disconnect the share screen.
Sure. Okay.
Okay.
I disconnected.
Okay. Thank you. So we would
Thank
like,
you, Choi-san. Thank you, Zhao-san. Thank you, Tan-san. Thank you, Shirini-san.
also the Professor Fukuda.
Ahad-san. Oh, you're here.
Waseda University professor, and I did not introduce. He is professor of Meijo University. Thank you very much. And we would like to move to the next presentation. And next is a study on the reliability evaluation of composite power system, including wind turbine generators, by Professor Seok Choi.